I'm going to use this version of it, which means for this particular function, I need to know what f of x plus h looks like. Well, notation-wise, this says wherever I had an x in the function, I'm going to replace it with x plus h. So I'm looking at a limit as h approaches 0. And instead of writing f of x plus h, I'm going to end up with the square root of x plus h minus 3, because I'm replacing the x with x plus h, minus f of x, which means I leave it alone. And then that whole thing is over h. Well, once we have that written, then it's just a regular limit problem. And we're going to use all the same tools that we would use with any other limit problem, which means that first step would be to plug in 0 for h, because that's the thing we're taking the limit of. But when you plug in 0 for h, you should always get 0 over 0 at this step. We're always going to have to do some more algebra. Because we have square roots, the algebra I'm going to want to do is to multiply by the conjugate. Which means that I change the sign between the square roots, not inside the square roots. And when we multiply by the conjugate, that means multiplying the top and the bottom by the same thing, so that I'm not actually like numerically changing the problem. We're just multiplying by 1 super creatively. From here, the objective is to get that h in the denominator to cancel out, which means I'm not going to multiply it through. I'm not going to like distribute this out. I want to leave it alone. I just want to clean up the numerator. Multiplying by the conjugate means, like, the whole reason we do that is sort of so those middle terms cancel out. So I'm going to have the square root of x plus h minus 3 times another square root of x plus h minus 3, and the square roots are going to cancel, so that I've got x plus h minus 3. And then minus the square root of x plus 3 times the square root of x plus 3, which gives me x minus 3. I've left everything in parentheses here just for kind of my own sake, to make sure that I remember to distribute that minus sign. You could definitely do that as one step and clean the top up at the, like, in the same step. But I'm going to have a limit as h approaches 0. And on the top now, it takes so much time just to keep rewriting this. Man, okay. So on the top, if I distribute that minus sign through, I've got x plus h minus 3 minus x plus 3. And if all has gone according to plan, everything on the top should cancel unless it has an h in it. And it looks like it worked out. My x and negative x, my negative 3 and 3, those are all gone, which means I've got h over h, or 1. I haven't actually evaluated the limit yet, so I'm going to write it one last time. But what we have done is gotten rid of that lone h in the denominator, which means I'm ready to evaluate the limit by plugging in 0 for h. And when we do that, I should have a square root of x minus 3 plus another square root of x minus 3. Or if you want, you can put those together and write it like this. Other questions? Yeah. So that's a great question. Is the answer we got m? So the answer we got is a rule for finding the slope. So now if I said, what is the slope of the tangent when x equals 5, then this is like a formula that gives me that m value. I would say m is equal to 1 over 2 times the square root of 5 minus 3. We call the power rule. And I'm going to just don't even like take notes on this for a second. We're just going to do a couple really quick. And you're going to be so good at this in 3 minutes that like, then you can put something in your notes. So if I had a function that looked like x cubed plus 6x squared minus 10x to the 4th, I'm just going to tell you what the derivative is. I'm going to give you a couple examples up here. And let me give us one more. And I'm going to let everybody stare at that for 15 seconds. You're using your keen powers of observation to find the pattern if you don't already know the pattern. And if you already know the pattern, you're going to use your keen powers of observation to affirm that yes, the pattern you see is correct. And then I'm going to take a brave volunteer who is willing to explain what the pattern is. Do I have any brave volunteers? We got a brave volunteer in the back. What's our pattern?
Okay, I really don't know this. So it looks like the power, you take the power and multiply it by the variable, and then you take that out of the power. Like, cancel that down, and then you take the power and you decrease the power. And then this for the fractions, you're doing the same. I don't know if I don't understand.
Cool. Okay. So for the sake of those who are on Zoom and probably couldn't hear that in the back, I'm going to do my best to try to repeat the awesome explanation that was just said. So we take the power and multiply it by the coefficient and then decrease the power by 1. So let's check that for these. So if I look at this first one, I'm going to take the power and multiply by the coefficient. So there's an invisible 1 in front of the x cubed. So I would have 3 times 1 and then decrease the power by 1. So 3 minus 1 gets us to 2. Or here, 6 times 2 gives me 12. And then we decrease the power by 1, but 2 minus 1, we don't usually write the 1. We could. Over here, 4 times 10, we get 40. We decrease the power by 1. Now, the truth is, I did the same thing to this last one. It's just fractions, and so our brains turn off when we see fractions. Okay, not everybody's brain turns off, but for some people, there's a part of your brain that turns off because there are fractions. So if I did this one in slow motion, like kind of going back, and I'll just take the 5x to the 1/2 part. So if I follow that rule, I take the power and I multiply it by the coefficient, and then I decrease the power by 1. I just kind of did all of this in one step. So 1/2 times 5 gave me the 5/2. And because I'm subtracting fractions, instead of thinking about that as a 1, I'm really thinking about that as 2 halves. So 1 minus 2 is giving me the -1 half. So it was messier, but it still worked. By the way, I did the same thing with the negative exponent. So I had 2x to the -3, which means I would have 2 times that power of -3. And then when we subtract 1 from the exponent, -3 minus 1 gives me -4. So that's the rule. And if we were to write that in a super mathy like formula way, I could say that if I have something that looks like a constant times x raised to a number, then the shortcut for my derivative is the constant times n times x to the n minus 1. And if you're going to put something in your notes, you could put that in your notes. But generically, it's like the rule for the slope of the tangent line. If we find it at a point, it actually is that slope for the tangent line, but whatever's going on, it's the slope of the tangent line. So don't think too hard. Don't use calculus. If I told you the f of x is equal to 3x minus 4, what's the slope? Totally. Well, that means the f prime is equal to 3. We'll come back to that in a second. If I told you the f of x was equal to 8, what kind of a line is that? Oh, I was thinking of where this starts with h. Yeah, it's totally a horizontal line. Well, if this is a horizontal line, what's the slope of a horizontal line? Right. Now, technically, both of these are still following that same power rule. We would just have to be weird about it to make it work. So this one, if I wanted to think about it as that power rule, I'd really have to come in and say the f of x is equal to 3x to the first power minus 4x to the 0 power. I would never do that. I am only showing this to you once, but if we followed that power rule, then this would look like 3 times 1 times x to the 0 minus 0 times 4 times x to the -1. That garbage is equal to 0. And x to the 0 is equal to 1. Don't think about it this way. If you wrote it, erase it. Don't think about it this way. You have skills. Don't lose the skills you already have. You know what the slope of a line is. You know how to spot it in an equation. It's the coefficient on the x. And you know that the slope of a horizontal line is equal to 0. So in terms of what our book gives this one a special name and calls it the constant rule. So if f of x is equal to a constant, then the derivative is equal to 0. I don't know why we even needed a special name for that. But technically we could give it a special name. Big step back framework of what we're being asked to do in this problem. We're being asked to find the equation of a line. So whatever else is going on, I'm going to start by getting my partial credit. I know what the equation of a line should look like. I know that the equation of that line ought to look like y minus y1 equals m times x minus x1. Question. Oh yeah, you could totally move the y1 over. You can totally make that y equals y1 plus m times x minus x1. Yeah, totally. You can also do y equals mx plus b. It's just almost always going to be more work given the information that we usually have in a calculus problem. This is almost always the easier option. So whichever one of these we want to look at, I I need a point and a slope. Doesn't matter which thing we find first. Let's deal with the point first because they gave us half a point. They gave us the x value. So if I go to find the point here, when x is -1, if I look at f of -1, I've got 3 times -1 squared plus 6 times -1 minus 12. -1 squared makes that positive. So that's 3 minus 6 minus 12. I think that's -15. So that means the point that we're plugging in has a y value of -15 and an x value of -1. Doesn't matter which one. If I go with the top version, that means I'd have y minus -15 is equal to m times x minus -1. If you went with the second version, we would have y equals -15 plus m times, and I'm going to take that minus and minus and go ahead and write it as a +1. Next piece of information I need is the slope. We are not going to use the limit definition of the derivative unless someone really, really, really wanted to practice it. But let's not. So to find that slope, I'm going to start by taking the derivative of the function. So my f prime, we're going to use that rule. So I'll take the power, multiply it by the coefficient, and decrease the power by 1. So 3 times 2, that's 6, x to the first power. And then for 6x, right, if I get rid of that first piece, the 3x squared, and I just look at the rest of it, 6x minus 12, I know what that slope is. It's 6. Anytime I have a constant times x, the derivative is just the constant. Anytime I have a constant, the derivative is 0. So my actual slope at the point where we care about it would be f prime at -1, which is 6 times -1 plus 6. I didn't do this on purpose, but we got a slope of 0. Cool. It's okay to get a slope of 0. If I stick that back into the equation, it just means that I'm going to end up with y is equal to -15 plus 0 times x plus 1, or y is -15. That's okay. I will pause there in case there are questions before we move on to another lovely one. Now I'm going to remind myself all the things we've got to be able to do. Yeah, so y equals -15 is the equation of the line. Which also tells me, if I'm thinking graphically about this, this was some sort of parabola that was concave up. So there's only one point on that parabola where the tangent line should be flat. So I know that I accidentally picked the x value at the vertex. Didn't do it on purpose, but I accidentally hit the x value at the vertex. Good times? Let's go ahead and do another one. Sometimes we have a problem where we are going to find our derivative using that power rule. It's just that the powers are kind of hiding from us. So I'm going to give us a slightly messy one. And this is going to look like the square root of x minus 3x squared all over x to the fourth. So if I want to take the derivative of this, I'm going to do some algebra first. There are more calculus-y ways through this problem, but I'm going to choose algebra over calculus nearly all of the time because we've been doing it longer. So what I mean by using algebra first instead of jumping right into the calculus is to rewrite this thing. So that square root of x, I'm going to rewrite to say x to the 1/2. The fact that both of these pieces are over x to the fourth, I'm going to break this up into two separate pieces, each over x to the fourth. Because now I can use, again, I haven't taken a derivative yet. I'm still just messing around with the function. I'm putting the function into an algebraically equivalent form. But now I can use my power rules. Oh, that was a bad choice of phrasing. Now I can use the additive law of exponents. So now if I'm using my exponent laws, because I'm dividing two things with the same base, I can subtract those exponents. Again, I'm not taking a derivative, I'm doing algebra. If I have 1/2 minus 4, that's going to be negative 7/2. X squared over x to the fourth, if I subtract those exponents, I'll have negative 3x to the negative 2. If we have it in a form where it looks like a number times x raised to a number, then we can apply our derivative power rule. Now I'm ready to take that derivative, where I bring that power down, multiply by the coefficient, and decrease the exponent by 1. So this would look like negative 7/2 minus 1. Here, I'd have the negative 2 times negative 3 would give me a positive 6. And when we subtract 1 from the exponent, I'll have negative 3. I am looking at negative 7/2 x to the negative 9/2 plus 6x to the negative 3. There are lots of different ways that you could choose to write that. But that's our derivative. And I would probably quit there if the question was to just find the derivative. As another, just like find the derivative, use some algebra kind of thing. Let's say I had 2x squared plus 1 times x minus 3. There is a calculus-y path through this problem. But if we do the algebra first before finding the derivative, I'm going to distribute this out. Yeah. Oh, yeah.
So if you were to use the quotient rule, would you get the same thing?
You should, but it won't look anything like this. Yeah, totally. So if I do some algebra to this before trying to do calculus, I can distribute this out. So I'll have 2x squared times x, get 2x cubed, 2x squared times negative 3, get negative 6x squared, 1 times x, 1 times negative 3, and then I can pop in and take a derivative. Multiply the power times the coefficient, reduce the power by 1. 12x to the 1, derivative of x is just whatever the coefficient in front of it is, which means it's an invisible 1 at the moment. And the derivative of negative 3 is 0. So thinking about continuity here, there are three pieces to our definition of continuity. I need the function to be defined at the point. I need the limits from the left and the right to match up. And I need that value for the limits to be equal to the value of the function. So when we have a piecewise function like this continuity question, the places where we need to check it are where the pieces are matching up. So in this case, I would need to check at x equals -1, and I would need to check at x equals 3. And we'd be looking at all those pieces for continuity. So, so if I check at -1, we need the function to be defined at -1, and it is because I have an or equal to component at an x value of -1. Same for the 3, it is defined at 3 because I have that or equal to component when x is trying to be 3. So f of -1 would tell me use the top piece. I'd get 5 minus -1, which is 6. Which is a number we're good, we're defined. At 3, if I looked for f of 3, I'd be using the bottom piece because that's where my or equal to is. And I'd have 2 times 3 plus 1. That's 7. It's a number, we're good. The next piece of this, and you are being graded on notation, so the next piece of it really does need to have the limits. So we're going to check the limit as x approaches -1 from the left. And we need to know, is that the same as the limit as x approaches -1 from the right? And here I'm looking at two different parts of the function on the left and the right. So on the left-hand side of -1, the part of the function I'd be looking at is the top part, because that's where x is less than or equal to -1. And I'd have a 5 minus x. On the right-hand side, I'd be looking at that middle part, the x squared minus x plus 6. Now, technically, the 2x plus 1 is also on the right-hand side, but it's like way over there on the right-hand side of -1. And with limits, we're thinking about getting really, really close to the number. So if we evaluate both of these, the question is, do they match? On the left-hand side, when I plug in -1, I've got 5 minus -1, which is 6. And on the right-hand side, I'd have -1 squared minus -1 plus 6. So that's 1 minus a -1 or 1 plus 1. So I think I'm looking at 2 plus 6. Am I doing the math right there? So they're not equal. So I know that this function is not continuous at -1. I will give you a minute to try the x equals 3 part on your paper. What's the verdict? Is it continuous at 3? I see some head shaking of a no, and I agree. Just for completeness, if I look at the limit as x approaches 3 from the left, the function I would be looking at is the x squared minus x plus 6. And we'd be checking, is that the same as the limit as x approaches 3 from the right? And on the right-hand side of 3, we should be using that 2x plus 1. So here I'd have 7. And the question is that the same as, 3 squared, that's 9, minus 3 takes me down to 6. So I think I get 12. They're not the same. So the question is asked as is f of x continuous for all values of x? The answer to that question as asked is no. If I had to give the intervals on which it is continuous, I would say that it is continuous from negative infinity to negative 1, from negative 1 to 3, and from 3 to positive infinity. Asked to find the vertical and horizontal asymptotes. Vertical asymptotes are candidates or what makes the denominator 0. But x squared plus 8 is never equal to 0. If I tried setting it equal to 0, I'd end up with x squared is equal to negative 8. That can't happen. So we actually for sure don't have vertical asymptotes. So now we switch gears and do the horizontal asymptote. And that one we are going to have. So for the horizontal asymptote, I'm always looking at the limit as x approaches infinity. Now, while the textbook gives us some shortcuts to determine what the horizontal asymptote is, I always err on the side of let's show our work, not just use the shortcuts. But does anybody know what the answer is going to be just by looking at the powers of x? So it's actually going to be 0. So if you didn't look at that and know, then definitely we want to show our work. So to find that horizontal asymptote, looking at that limit as x approaches infinity. By the way, the horizontal asymptote stuff, vertical and horizontal asymptotes, that's section 3.6 of our textbook. So if you're like trying to figure out where this is in the book, 3.6. So I'm looking at the limit as x approaches infinity. We've got negative 3x over x squared plus 8. And what I'm going to choose to do is to find the largest power of x in the denominator. I will always choose the denominator. So my largest power of x here is x squared. We have two choices. We either divide every term by x squared, or we factor an x squared out, but then we do really weird factoring. So I've kind of settled on divide everything on top by x squared, dividing everything on the bottom by x squared. So if I kind of distribute that out, then in my numerator, I'm going to do an extra step. You can skip this step and go straight to simplification. But since we haven't done one of these in a little while, I'm going to go ahead and write out that intermediate step. So that's what we're doing to each of the terms. And then if I simplify stuff, again, I'm not evaluating the limit yet, so I still want to write that, making sure that I'm getting all my points. But if I simplify this, I've got negative 3 over x on the top. On the bottom, x squared over x squared is 1. And then I've got 8 over x squared. Well, the magic trick here is that a number divided by infinity is headed to 0. Because no matter how big that number is, infinity is way, 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 way bigger. So the top is headed to 0, and 8 over x squared is headed to 0. So this is really like I have 0 over 1 plus 0, which is 0. It's not undefined. 0 divided by a number is 0. Which also means that the equation for that horizontal asymptote would be y equals 0. That's a little gross, but not like crazy gross. I tend to start with vertical asymptotes just because there's kind of less work to do for vertical asymptotes. So my candidates for vertical asymptotes are whatever makes the bottom 0. Well, 4x squared minus 9 being equal to 0. I know I gave us fractions, but they're not like super gross. X squared is 9 over 4, which means I'm going to get positive 3/2 and negative 3/2 as our candidates for vertical asymptotes. In order to actually be a vertical asymptote, we just have to take the limit and get a number over 0. If we get 0 over 0, we got to do some algebra. It's probably not a vertical asymptote. But as long as we get a number over 0, it was a vertical asymptote. We can move on with our lives. So I'm going to check as x approaches 3/2. X squared plus 1 over 4x squared minus 9. And by the way, we just did the math. We already know the bottom is 0. You shouldn't need to do the math again. You just did it. But the top, I should plug in the 3/2 and just make sure that I get a number. It doesn't matter what the number is, so I don't have to simplify it, right? 3/2 squared, that's 9/4 plus 1. I don't like have to figure out what that fraction is. I got a number over 0. This is a vertical asymptote. This is headed to infinity. Now, technically, we could check whether it's headed to positive or negative infinity. But if the only question was, is it a vertical asymptote? I already know x equals 3/2 is a vertical asymptote. Now, if we do the same thing with x going to negative 3/2, we actually will get exactly the same answer. I'm going to be lazy, just call that f of x. We know we get 0 on the bottom. We get 9/4 plus 1 on the top again, because negative 3/2 times negative 3/2 is still positive 9/4. I get a number over 0. So x equals negative 3/2 is a vertical asymptote. For that horizontal asymptote, my powers on the top and the bottom match. So this is the one where we can use the coefficients to get the answer. So the answer should be 1/4. If we're going to show some work for that and look at the limit as x approaches infinity, I'm going to go ahead and skip to the step where I'm dividing every term by x squared, because that's my biggest power of x in the denominator. So if I divide every term by x squared, so I've got x squared over x squared plus 1 over x squared, 4x squared over x squared minus 9 over x squared. That is looking like 1 plus 0 over 4 minus 0, or 1/4, which means y equals 1/4 is a horizontal asymptote. I'm going to do this with the limit definition of the derivative. Please do not try to take notes on this. The algebra is going to get messy. I'm going to write a lot faster than you are, and no one's ever going to ask you to do this again. Okay, but I want you to see where it's coming from at least once, and it's good practice with the limit definition of the derivative. So here's what my situation is. I've got some function, S for Sara, cool, there's my function. And it's really like one function times another function. So imagine maybe this is like S of x is equal to 3x squared plus 4 times 6x minus x to the 5th. So I've got two functions multiplied together. And I'm going to use the limit definition of the derivative just because I can. So what that would look like for this thing is I'm going to have the limit as h approaches 0 of s of x plus h minus s of x all over h. But I'm going to go ahead and plug that into my function, weird as it looks, so that I've got the limit as h approaches 0. Plugging in x plus h everywhere up here would look like f of x plus h times g of x plus h. And then plugging in my s of x would look like f of x times g of x all over h. Now, the first thing that we would try with any limit problem is to plug the value in. But if I plug in 0 for h, oh wait, I lost an h, didn't I? Plus h. But if I plug in 0 for h here and here, then on the top I'd have basically f times g minus f times g. I'd get 0. So some clever mathematicians stared at that for a really long time. Heck, they probably got their PhD for it or something. We get the benefit of their staring at it for a long time. And they're like, yeah, we just have to add 0. Here's how they added 0. They took that f of x plus h, g of x plus h, and they said, just for funsies, let's go ahead and subtract off f of x times g of x plus h. But then, because we don't want to mess up the problem, we're going to add it back in again. And don't forget about that minus f of x, g of x we had in the first place. Whole thing all over h. So this part in the middle here, oops, adds up to 0. But what this clever mathematician saw is that now if I break this apart into two pieces, like all of this, that pen's not showing up super well, but all of this and all of this, and we write those as two separate pieces, magic happens. From these first two, they both have that g of x plus h in common. So I'm going to kind of factor it out. So I'd have like the f of x plus h minus f of x, but then we'd have g of x plus h. And that whole thing is over h. And then for the second piece, we're going to do the same thing, but what they have in common is f of x. And then we'd have g of x plus h minus g of x all over h. And then clever mathematician said, oh wait, we know what two of those things are. We've seen this thing before. The limit as h approaches 0 of f of x plus h minus f of x all over h, that's f prime. And when we plug in 0 for h over here, that just turns into g of x. Back here, I've got that f of x sitting around by itself. And the limit as h approaches 0 of g of x plus h minus g of x all over h is g prime. That's the product rule. And now let me quickly get it off the screen so no one is tempted to write out that garbage. And then I'll tell you what you are going to write in your notes and we'll do some practice problems. So what our product rule, I promise I'll put the notes in Canvas. It'll have all that work on it. But what our product rule says, and this is how I remember it, my good friend Lola taught me this trick. It helped me to memorize it. If I have f times g and I want to take the derivative, and I'm using that notation of like putting the prime up there to mean the derivative. If I have f times g and I take the derivative, well, I had two letters, f and g, so I'll write it twice. What usually goes with multiplication? Addition. And then we chase down the derivative. Now, the nice thing about thinking about it that way is now if I add another letter, like if I have f times g times h, like I have three functions that are multiplied together. Since I had three functions, I would write it 3 times. I would say what usually goes with multiplication, addition. And then I chase down the derivative. This is something that should be on your card or your page of notes or cemented in your mind somewhere. This is something that we're going to want to memorize. Or because you have the convenience of a note card or a page of notes, something that you should for sure put on it. So let's go back, and I had one that we didn't do as a product rule but could have. So let me go back and take back in time to, I don't know, 20 minutes ago. I had this function that looked like 2x squared plus 1 times x minus 3. I still think the way we did it was faster, but we could have done this as a product rule, where I'm saying all of this stuff is f and all of this stuff is g. So when I go to take the derivative, in terms of our product rule formula, I know I'm going to have 2 pieces multiplied together plus 2 pieces multiplied together. And I'm just going to write out the pieces of the formula. F prime times g plus f times g prime. And then I'm going to fill in each part. F prime means take the derivative of this piece. Well, 2x squared plus 1, if I take that derivative, I get 4x plus 0. And then we leave g alone. And then we leave f alone. And then we multiply by the derivative of g. And the derivative of x minus 3 is 1.